Geo Interviews podcast. Today we have for the first time not one but two guests in a discussion split into three parts. Helen Rogers, Chair of the Institute of Physics Environmental Physics Group and consultant in education and atmospheric science, is joined by returning guest Luthais McCash, Chair of the Mathematical and Theoretical Physics Group at the Institute of Physics and Chief Scientific Officer at Sigma Solutions. Loads more information about each of the guests can be found in the description, as their accolades are too numerous to fit into a brief introduction. In part one of this series, we discuss interdisciplinary science. In the second, environmental physics, and in the last part of this series, we discuss some of the big questions of physics education. Enjoy. Right, so I think a really good place to start for this section is just what is environmental physics?
I think answers on a postcard, please, because environmental physics means something different to everyone. To me, I'm an atmospheric physicist. I can class myself in the group of environmental scientists. But equally, you could be an atmospheric chemist, you could be a geologist, you could be a geophysicist, you could be someone who's interested in the migration of butterflies. You know, so many things relate to the environment, and that's both a lovely, therefore, catch-all, but also quite a dangerous term to use, I think. I say that as the chair of the Environmental Physics Group for the Institute of Physics, so I'm in a slightly precarious position. But I think, to me, it's about the world we live in, and it's about maintaining the world we live in. So understanding it in order to maintain it. And in that regard, it does encompass so many of the things we talked about with regard to interdisciplinary science. It covers that entire breadth. And of course, again, it goes beyond science. It's just simply an interdisciplinary subject. Right. I think the problem with the definition, which is so broad, is that it's everyone feels inclusive, but it means it's very hard to sort of really tap down to who is sort of leading the way in the environmental science field, for example, without simply being somebody who simply has, dare I say it, an opinion. As scientists, we tend to deal in facts or predictions, but quite quantitatively rather than on a qualitative approach. And I think everyone who does something to support and help the environment, that's absolutely brilliant, be it you're recycling or reducing energy usage through switching off light bulbs, whatever that might be. But I think it sometimes can be slightly dangerous because therefore everyone feels as though they have a justifiable reason for taking a stance that they take. And again, the internet is a marvelous thing, but it can also be quite damaging and misleading, because it gives an opportunity for people to express opinions that are qualitative rather than quantitatively based. I think within the climate change environment, it has been really misleading in the past and really negative in the past, because I think often it's portrayed, when scientists have a difference of opinion as to what the environmental impact might be of climate change in the future, that's simply saying that I have a computer model that will predict a certain temperature change, let's say in 50 years. You, on the other hand, may have an equally good model based on similar premises, so similar equations we talked about before, the Navier-Stokes and so forth. Maybe your focus is a little bit more on the boundary layer rather than the upper troposphere or the lower stratosphere, different parts of the atmosphere, but it's still a good model. And you would come out with maybe a slightly different temperature change. over 50 years. Now, that doesn't mean that we don't know the answer. And often climate skeptics portray that as a lack of understanding by the science community. That's not the case. That's simply saying that we internally know that there's a variability in the system. I mean, after all, it's -3 degrees outside for me today. I think they're predicting 13 degrees next week. That's not saying we don't understand and know how our atmosphere works. That's simply saying that there is a variability associated with it. Now, there'll also be, as well as a natural variability, a variability associated with those computer models. They each focus on a different element. They'll have different strengths and weaknesses. They are providing indicators. And actually, I'd be more worried if they all gave exactly the same number than them giving a range. A range doesn't mean that we don't know, as I keep coming back to. It simply says that there is a degree of variability. And so, again, within environmental science, that's often hard to articulate. And I've no doubt it's the same for various different branches of physics and other sciences within environmental science. And together it can therefore become a little bit of a mixed bag of stew as such. You know, you can have different bits floating around. Actually, the individual science communities will understand their strengths and weaknesses, but it's quantitatively driven, not qualitatively driven. And there's sort of, as I say, there are both positives and negatives to that term, environmental science.
Right.
I think.
Yeah, go on.
Sorry, Casper. I just I think as well that the scientific community as a community accepts that there will, as Helen said, be variability in these models. And actually, when you write scientific papers and you give a graph, for example, you know, what really you should be quoting within this when you're discussing your results is, well, here's my error bars on my model, or here's the variance. And we're quite content at being able to say, yes, we think the value might be 10 plus minus 5% or something like that, and we're all right with that. But as Helen said, within the media, there's often this portrayal of oh, well, one scientist said this and another scientist said that, and you will find cases where there are things that are just directly orthogonal to each other. But generally speaking, when you're discussing things in the same kind of remit, it really is dependent on the models. And coming back to what Helen was saying about the environmental physics and environmental science being a overriding term, even if you look at something like climate change versus global warming, they are different things, but they're portrayed on a public understanding basis of being the same, and they're not the same. And so what you often can get is, for example, global warming or climate change skeptics that will take out a graph and say, oh, well, there was a pause here and this was an El Nino year, and they don't really have an understanding of what goes on. And I think that sometimes the ability for scientists to communicate these things to the general public is not always as effective as it could be. And so in that sense, we do ourselves a discredit as scientists, because we can't or don't or portray or come across environments, no pun intended, but environments where we can actually discuss that in a way that is comprehensible sometimes. And yes, it is true. I think it was an economist, George Box, I think 1920s, 1930s, I think, said almost all models are wrong, but some models are useful. And this is often an argument I get from people when we're talking about predictions, as Helen alluded to. And I say, well, yes, it is a prediction. We have a very robust scientific method in order to make that prediction. But if we don't make a prediction, what else can you do? there's not actually much you can do other than to say, based on the scientific method that's been devised over hundreds and hundreds of years, by looking at the data and looking at these models, we make a prediction on what something might be like at a later time. And if we don't do that, my argument is, what's your alternative? What are you suggesting?
The atmosphere is a single test tube. It's our world is a single test tube. We don't have multiple test tubes. We can't go, well, hang on, what if we take out this? What happens? What if we put this in? What happens? Because it's done. It's too late if we try and do that sort of thing. So actually models help us to understand what each of the components do and their relevance and their importance, so that if we change them, we know what the outcome. So it's rather than having a single real test tube, we've got hundreds and hundreds of virtual ones which we can play around with and which we can change. And that's what predictive modeling enables us to do. And of course, what we could do is we could go back in time as such and predict going forward to the present day and check. And that's something we do quite routinely as well. So that's always important, and that's why we use things like ice core samples and so forth to go back as well as to go forward. But yes, I mean, we haven't always been the best at communicating, and I think there have been other lobby groups out there that have been better at doing it. And I think, again, this probably now moves into the education as well element again, so I won't dwell on it for too long, but it's about helping people understand, as we've discussed, these error bars. If it's actually an error, again, even our language isn't always helpful. An error implies that it's wrong by that much. Actually, no, it's that the range of our results are within this band. And it's a totally different thing, really. And so we need to be clear, and we need to be concise about how we deal with our data and what it really means, to avoid the whole sort of climate skepticism and so forth. And that's I say this from a climate perspective, because we saw exactly the same thing going back again then to COVID over sort of vaccinations, and we've seen that with MMR vaccinations, for example, and so forth. I think it's about communicating the science, and that's where there is a danger out there of people utilizing information not necessarily for the right purpose, for the right use. They don't necessarily know the premises that have gone into it. And so, data is a fantastic thing in the right hands, but it can also be a real danger as well. And we need to always look at things with a slightly skeptical eye.
I think as a complete layperson myself as well, it seems like when things have happened, or when we're talking about climate change or COVID or anything in that sort of realm, there will be 100 studies or whatever predicting some range of results, and then one study that is some anomaly outside of that, and that's the one that then gets shared on social media as a layperson. In terms of what I've seen, that it seems to be a slightly unhelpful phenomenon that certain people will just believe one result and confirmation bias will kick in. And I guess that's moving on more to the education of science. But
coming back, I think, as well to what I said about the scientific method a few moments ago, is that it's very, very easy for people to form an opinion and then look for the data that backs up that opinion.
Yeah,
that's very, very easy to do. And this links to a wider thing, which is actually something that Neil deGrasse Tyson mentioned a few years ago. And it was that one of the great difficulties in the world is knowing enough about a subject to convince yourself you're right, but not enough about a subject to be able to convince yourself you're wrong. And it's a very powerful statement, and it's a very important statement, but it does relate to this kind of discussion in terms of that cross between the scientific articulation of what's happening and how we arrive at these things versus the understanding of what that scientific articulation are. And I think there is quite a large gap between them. And so often what you can find is people who read a lot online and believe that they've educated themselves, when actually they're very, very superficial in their understanding of science, but nonetheless they've convinced themselves that they know enough in order to form, as Helen said, an opinion.
Yeah, and this comes back again to communication internally as well within physics community. So what you won't see when you see results come from things like the Intergovernmental Panel on Climate Change, so IPCC, when they publish their big reports, you won't see all of the debate that happens behind that. And that, I use the word debate carefully, because we're very good at scientists. I mean, by our very nature, we've demonstrated that curiosity often. And so we're interested in other people's results, and we do push against them. That's not because we don't believe them or whatever else, but we want to understand more, and we want to test, and we want to understand why our results differ. Again, that's not a negative, and sometimes that can be portrayed as such. If you say, oh well, these there's a big argument between these two places or these two groups who are doing some work, that can be viewed as negative. Actually, from a science perspective, that's what we scientists do. We argue about pretty much everything, because it's our form of pushing and demonstrating curiosity and our level of intrigue into something. We want to understand it, and part of our understanding it is to test it. It's no different than a baby who is looking to eat food for the first time. They test it. They test everything, whether you like it or not, and that's what we do as scientists, and that's a good thing. And again, sometimes these dialogues can be portrayed as negative, but actually it's a good thing, and it demonstrates again our curiosity. And when we present something then as a community, such as the IPCC, there's a lot of rigor that goes into that, because we have all pushed against one another, and we've had to articulate, and we've had to convince other scientists of our results, and that's a positive thing, and that strengthens our argument, not weakens it.
So I think that leads on. I know you mentioned that we already have a pretty good understanding of our atmosphere, and we kind of understand the system pretty well. But what are those areas where there are still things to be understood? What are the challenges? What needs to be resolved? What are the important things that current research is looking into in atmospheric physics?
Oh, I think we're a long way from understanding everything. We will never understand everything. You only have to look at weather predictions. How accurate is your weather forecast for where you live? It's probably all right, but there'll probably be days when it doesn't rain and it says it's going to rain. And that in itself is an atmospheric model. And it demonstrates...
Unless you're in Scotland, sorry, and if it says it's going to rain, it will definitely rain in Scotland. In fact, even when it says it's fair, it will probably still rain in Scotland. Well, that's the only, there's a 1 probability that it will rain in Scotland every day. Rain and be cold.
But it's, that level of difference between what you're experiencing and what the weather forecasters predict just goes to show actually the level of variability in the models. Now, can we reduce that variability? Yes. Modeling has improved significantly with computational power. So the way that often the models are done is on a very small grid scale. And not many decades ago, Scotland would have been one grid box. So you don't get any variability. You just get the weather in Scotland is going to be rain. Okay, fine. But you can't narrow it down. You need the extra computational power to be able to make those grid boxes smaller. And not just smaller in terms of geographical surface area, but also in terms of altitude. Because what happens in the atmosphere, it's a 3-dimensional situation. It's not just our weather. There are various different layers. And so computational improvements are allowed us to to reduce that grid scale. And also now, when I started my research, it was just at the time when chemistry was being included within physics models of the atmosphere. And of course, there's feedbacks. There's feedbacks between, if you suddenly have more ozone, well, you're going to change the heat at the surface. And that in itself then will change the physics because of all the latent heat and whatever else. And so you have these feedbacks. And that's without including then the biological process at the surface. If you have a certain crop versus, for example, a lake, you have a different what's called an albedo. So that's light that's reflected. And that, in effect, then will change the temperature profile above the surface, which then feeds back into the chemistry, which feeds back into the physics. And these are all interrelated.
And again, it supports the idea, sorry, Helen, that also supports the idea we were talking about earlier about that interdisciplinary side of science. We can't do it all on our own. No. we need to collaborate with people.
Exactly, and all the experts in these different fields. And then that even comes down to, for example, architects as to city planning, because the city structure will impact the atmosphere that's above it and so on and so forth. So you can start to see the scale at which atmospheric modelling takes on a life of its own. I mean, you think about SimCity, this is SimCity and some, it's an immense task, and therefore it's not surprising that we don't always get it absolutely right. So in terms of what's happening next within the environmental or within atmospheric science, let's put it within that aspect to begin with, we're still working on a lot of the chemistry nuances, reducing those grid box scales, and that's with computational power, feedback systems. Ultimately, the higher in the atmosphere we can go with our models, the better, because we include more information. Again, that requires the computational elements. We need to work more and more in an interdisciplinary approach to include it. So there are always additions. And then we need to work at the perturbations, so that if I fly an aircraft and I'm suddenly putting an emission at altitude, how does that impact? And so on and so forth. It's an incredibly complex situation. And the other thing is, because we've talked a lot about modelling, but we haven't talked about measurements. And we need to make appropriate measurements of the atmosphere in various different locations in the atmosphere, in order to validate our models, to understand fully what's happening, to look at things in more depth. And the atmosphere is a slightly difficult one, because you could say, well, yes, use satellite data. Well, that's great for some things. But the further down the atmosphere, sometimes the harder it is to pick up the signal. And equally, if you're at the surface looking up, the further up in the atmosphere you go, the harder it is to pick up the signal. And so you've sort of got a band in the middle, right in the sweet spot of the atmosphere, where it's actually quite difficult to make measurements. And so we need to think about how we do that in the future. It's not that long ago that suddenly the ozone hole appeared, and took everyone by surprise, except for the people who were making measurements in the Antarctic, who were sort of seeing these regular low levels of ozone. And our understanding, so we had to respond quickly to that. We had the whole CFC issues and everything else. And actually, in the grand scheme of things, atmospheric science and particularly around climate change is a very new science. So there's a tremendous amount of work there to be done, not only in terms, as I say, of the modelling aspects, but actually in terms of measurements, getting long enough data sets, and so forth. So there's a lot of work still to be done there.
As a sort of far off question, quite speculative into the future, is it conceivably possible to simulate sort of the entire atmosphere perfectly and make perfect weather predictions without having to simulate the entire system down to like the subatomic level. I mean, you're speaking about a lot coming into this, down to buildings, down to planes. Is there a limit on how good we can make our models without just simulating the entire thing?
I mean, I think what you're kind of referring to there is almost this idea of emergence phenomena, right? The idea that rather than look at things at the most kind of, as you described, subatomic level, look at the system as a whole. Part of, I think, the difficulty in this is that in some ways the models that you use are only ever going to be as good as the data that you get. So that, I think, is certainly a limitation on models in general. So if you don't have good data or reliable data from which you can build up these models or test these models against, that poses a challenge, I think, is kind of from a data stroke measurement point of view. And then on a more general point of view, I think that the evolution of atmospheric changes or the weather, for example, is occurring at quite a fast rate. I think that we're a little bit probably behind the curve in that there would need to be such a mass effort to get to where kind of Earth's atmosphere is at the moment, if you like, in order to then actually be able to effectively measure that going forward or predict that going forward, in the context that you're asking, which is everything as a whole. So but again, Helen, you this is your area a lot more than it is mine, but my intuitive feeling is that I don't think we'll ever get to a point where we can precisely and accurately model every element of the system and describe that system as a whole system in, I think, the way that I understand you to be asking the question.
Yeah, I mean, I think, there's this sort of statement that, a butterfly flaps its wings in America, and you have a hurricane in, across the other side of the world. And that's an extreme. But these are small differences can make a large impact. We do another type of modelling rather than trying to look at everything as in precise detail, whereby we have effectively a cluster of models where we run them all, and there'll be thousands and thousands of different modelling approaches. And the idea is that effectively, by knowing the range of answers, you might find that you don't need to model a butterfly's wings, because if you're actually not looking to see what the wind speed is next to the butterfly, but you actually just want to know the temperature change over the entire Earth system, well, you don't need to know that level of detail necessarily. And by doing these ensemble modelling approaches, you can demonstrate whether that's a need. It's also worth pointing out that actually we do a lot of modelling of planets as well, because planets are a great way of actually sort of having another test tube, in effect, a test tube that looks slightly different, maybe has will definitely have a different geography to it. It will have it'll have different flow of air and so forth. And so you can learn a lot from that. So, for example, on Mars, we look a lot at the winds there, because that sort of helps us with actually understanding how the wind crosses the Atlantic. There's sort of synergies between the two. So we can use other places, but in terms of modelling, I think it's going to be a variety of different approaches are going to give us a variety of answers. We're never going to get a single answer, and this is where it's important to appreciate that from the offset, and not to get too worried about it.
Right.
Just on that point as well. Again, not to go too much into the next section, but I think one of the things about educating in physics and mathematics and just general sciences is that certainly at high school, people are trained to love the answer. There's one answer in the back of the textbook. And actually, science isn't like that. And it comes back to what I said in the first part about interdisciplinary science and going into science accepting that you might not always be right, or you might get things wrong. And so I think that, again, Helen makes a really good point about the fact that we're not going to get one answer. And actually, if every single person got exactly the same answer, that would be more worrying than different people getting slightly different answers, actually. Not least for the fact that it wouldn't motivate maybe the same kind of discussions, which gives us on that interdisciplinary level that breakthrough, between different fields.
Okay, so I think that's probably one final comment on sort of environmental physics before we move on to the next section. Maybe a piece of advice to someone wanting to find out more about environmental physics. Where's the best place to start?
Not Wikipedia.
There are learned societies out there, such as the Institute of Physics and such as places like the Royal Meteorological Society, that will provide useful starting points for atmospheric sciences. Similarly, if you're looking at geological aspects, there's the Real Geological Society and so forth. They're often good launch pads into other things. And I think, actually the IPCC reports are very good, and their summary for policymakers is actually written in a language for the layman on the street, if you want to call them that, the people who haven't got a science research element to their career. And so they're actually really good places to start. Look at the summary for policymakers for the IPCC if you want to really sort of know where the consensus of scientific opinion is currently situated. If you start broadening that umbrella further, then again, you need to look more into, I would go to the learned societies and use that, as I say, as a platform to look further. So if you want to look at what opportunities there are within engineering or so forth, to look at battery storage, to look at new forms of transport, to look at new buildings, go to the learned societies and use that as a launch pad. Don't just trust it because your friend says it. And even if my friend happens to be a professor at wherever, I still won't necessarily trust it. You push back and you question. And that's about, again, eyes open, mind open, and don't be afraid to question things you see. And certainly, I think that's the important thing.
Awesome. Well, that's definitely, to anyone watching, a very useful thing to go and find out about. But we'll be speaking more about physics education in the next section. I hope you enjoyed that as much as I did, and I hope you're able to check out the other 2 episodes in this series, as well as the other Galileo interviews. Please like, share and subscribe. Thank you for your support, and see you in the next episode.